Alright. So, the next thing is the next controlled source is the voltage controlled current source, okay, and ideally quick, what is the input impedance of a voltage controlled current source? Infinite, R out infinite, okay, and the only other parameter that you need to define is the transconductance, right. IO is nothing but some Vi by R. So, 1 by R is often called the transconductance. So, again let us start using by using first principles. So, we want to generate a current IO which is controlled by this voltage Vi. So, we have some source Vi possibly with some resistance Rs. Okay. What all would we need to realize a current which is, if you are in the lab and if you want to realize a current which is Vi by R, what will you do? Okay, you need you need a current. So, does it make sense to use a variable voltage source or a variable current source? We have a variable current source, okay, alright. So, this is my variable current source, alright. So, what? We have this variable current source, we have the input voltage. So, what are we trying to do? Compare? Okay. So, one way of doing this is to put an ammeter here and that will measure the output current Ix. You compare it with, so you need to put a voltmeter here. No, what are we going to do? We have a voltmeter, we have a ammeter. What are you going to do now? Okay, so now you need a calculator to divide the voltmeter reading by R, because you can't compare volts with amps. It's like comparing apples with oranges, correct? So, what are we going to do? We need a calculator to now do V by R. Okay, now can somebody more come up with a more practical approach where we get rid of 2 meters and a calculator? Well, the suggestion is okay. That's the earlier scheme seems too complicated. Okay, so well, to multiply, to divide a voltage by a resistor is equivalent to multiplying the current. Basically comparing Vi by R with IO is equivalent to comparing Vi and I naught times R. Okay, so basically in this case, let us call this IO. This voltage is I times R. At least now we can get rid of the calculator. What else do we can we do? So, what are we comparing? We are comparing Vi with I naught R. So, that basically means we need 1 voltmeter to measure Vi, 1 voltmeter to measure I naught R. Can somebody think of a smarter way of doing it? So, basically rather than compare Vi with I naught R, we will compare Vi minus I naught R with 0. Alright. So, where are we going to put the voltmeter? We are going to put the voltmeter here, plus minus. Okay. So, if Vi minus I naught R is greater than 0, what does it mean? Means that I naught is too small and therefore must increase I naught. On the other hand, If it's less than 0, it means that I naught is too much, you must reduce I. So, in other words, I naught is dependent on Vi minus I naught R. The constant of proportionality is conductance, and how much must that conductance be? Some Gm, and Gm must ideally be, why? Ideally Gm must be infinite, because even for an infinitesimally small difference between Vi and I naught R, the current source must kick that output node so hard that I naught R will become equal to Vi. And so, what is the sign of that Gm? Plus or minus? So, if Vi minus I naught R is greater than 0, you must increase it. So, the Gm has a positive sign, all right. So, now, so therefore, this is a voltage controlled current source, okay. And so, now can we identify the transistor source? So, in other words, the incremental diagram this is Vi, this is R, and which is the output? This is the all right. So, this is our voltage controlled current source. Okay. So, what is Ri? The input resistance, it is infinite. Is that clear? What is the output resistance? Why? Okay, well, okay. So what? Okay, like the incremental circuit is here, all right. Okay, so we are trying to find the output resistance looking in here. Okay, so how will we do it? We de-energize all the independent sources, so this becomes 0. So, what Vi becomes 0, all right. So, therefore, this Gm becomes Gm times 0 minus I naught R. So, the direction of the arrow goes the other way. So, this is Gm times I naught times R, okay, all right. Now, what? So, what do? We want to put a V test here and find the current flowing, okay. So, let us do that. What is the unknown? Yeah, I naught is unknown, or I naught R, basically the potential of this node is unknown, okay. So, how will you find the potential of that node? So, basically the voltage at the source is therefore, what is the voltage at the source? Okay. So, what is the I test? What is I test? So, basically I test is 0. So, what is the output resistance? No, the load current depends on Vi, right. 1 plus 2 is 3, the sun rises in the east, all these are true statements, but they don't explain the fact. That is my trouble. The question I am asking is, well, it is true that the output resistance is infinite, the math proves it, correct, but the question I am asking you is, why does it make intuitive sense, or does it make any intuitive sense? In a MOS transistor operating in saturation, what comment can you make about the influence of the drain potential on the drain current? That is all that you need to recognize that the output resistance must be infinite, correct? Okay. The drain current of the MOSFET is not influenced by the potential of the drain, period, right? At least in our ideal model of the MOSFET, which only consists of a voltage controlled current source. Okay. So, and what is the transconductance now? IO by Vi is what? How can it be 1? IO is in amperes, Vi is in volts. No, correctly. What is the incremental voltage at the source? I mean, this does not require any new analysis, we have already done it before. What is it? Gm by? Hey, this does not even have dimensions of times what? No, this does not have dimensions of voltage. GMR by 1 plus GMR times Vi. Okay, so what is IO? Vi by, I mean this voltage divided by R. Okay, so this is nothing but 1 by R times, I prefer to write it this way because it shows you something, times Vi. Alright, and remember that sanity check. What is sanity check? Pardon? One sanity check is when Gm tends to infinity, you must get 1 by R. Alright. Okay. What is the other sanity check? When you put R equal to 0, what must you get? GMVI. When R equal to 0, the source is grounded, so you must get, it is the common source amplifier, right, common source type of configuration, therefore IO must be Gm times Pi. Clear? Excellent. So, so what does now large Gm mean? We said Gm must be infinity, Gm evidently cannot be infinite, so Gm must be large. So, what is it, what is the meaning of large now? Gm must be much larger than 1 over R. And if GMR is much larger than 1, as promised, the transconductance, which is the ratio of the incremental drain current to the incremental gate voltage, is largely independent. It is 1 by R times a large number by a large number plus 1, which basically is close to 1. So, even if the Gm changes by quite a bit, you can see that GMR by GMR plus 1 is not changing that much. If so, say for example, if GMR is 20, right, then it's this thing is 1 by R times 20 by 21, which is 0.95, right. On the other hand, if that Gm goes down even by a factor of 2, right, which is a huge change, right, then GMR becomes whatever, GMR becomes 10, 10 by 11 is 0.91, okay. So, even though you have a 100% change in Gm, the change in gain is only less than, is about 4%, right, okay. So, so this is the incremental network. So, now you are all experts at biasing the transistor and making it work. So, what do you think, what is your favorite way of biasing the transistor? Okay, you hold the gate at some R1, R2, all right. And what else? Now resistor ladder is done. What am I doing with the transistor? Okay, so you want to put a current source, fine. All right. All right, we pardon? I mean, what is the drain doing? What should I do? What do we do here? Ground it. So, in the real circuit, connect to VD. Okay, all right. And then what are we going to do now? Connect an R parallel to Iref. Okay, one suggestion is to do this with a through a capacitor. Okay. And why do we need the infinite capacitor? So that we don't mess with the operating point. An alternative thing to do would have been to remove the Iref and put the R there itself. Okay. So R basically not only appears in the small signal picture, but also appears in the quiescent operating. Okay. All right. Then what else? So again, we have our input Ri, Vi. This is the infinite capacitor, and therefore, if GM is large, what comment can you make about the incremental output current? If GM is large, the incremental current is approximately Vi by R. Of course, there is no point in generating an incremental, a current and dumping it into the supply voltage. So current is useful only when it is just like how a voltage, it does not make sense to have a battery and not load it at all, correct? Okay. You are not going to look at the battery and admire it, you need it to power a circuit, right. So similarly, you need this current to do something, and what is that something? You should connect a load. So basically some RL here. And what comment can you make about the incremental voltage across the at the drain of the transistor? Yes. What is the incremental voltage at the drain of the transistor? Minus I naught RL, which is I naught is known to be approximately minus Vi, Vi by R minus I times R. So, this is nothing but the incremental current I. Does that make sense, people? All right. Okay, so the next controlled source is the current controlled voltage source. Ideally, what are the input impedance? 0. Output resistance? 0. What is the only thing that we need to specify therefore? Trans resistance. So, VO by I in must be some R, and this is also called either the trans resistance or the trans impedance, it does not matter. And why trans? Because voltage by current at the same port is basically resistance. Here voltage is somewhere, current is somewhere else. So, it is transfer resistance or trans resistance. All right. And so, again we get back to our good old common sense approach. If you are in a lab, you want a voltage source we want an output voltage across some load which must be we want it to be equal to In times R. We have seen this before in the context of an op amp network, correct? All right. So, how did we do that before? What did we do earlier? Okay, so we said okay, we are going to have a variable voltage source in a way. I mean that's the method to vary output voltage, and we are going to compare. So we need to compute. We need to compare VO minus INR with 0, right? So if VO minus I, so how do we generate VO minus In times R? How do we generate VO minus In times R? We discussed this before. So this is R, this is In. So what is that voltage? V naught minus In times R, and if that is greater than 0, it means In is what it is. It means V naught is too much and therefore must, all right, and if it is less than 0, it must that V naught must be pushed up, all right. So, in other words, this VO is controlled by the voltage In times R. So, we can, I mean all right, but unfortunately our transistor is not a voltage controlled voltage source, it is a voltage controlled current source. So, in other words, rather than change the potential of node VO by using a variable voltage source, we have to use a variable current source. So, basically okay, all right. So, I think it is late, we will continue with this.